Hello and welcome to another episode from Spiral Physics Education. In this episode, we'll be looking at different models of the atom that start from the Plum Pudding model. And we're going to be also looking at the alpha scattering experiment, which led to Rutherford's model of the atom. We're also going to be looking at the Bohr model of the atom and also about the diameters of the nucleus and the atom. So let's get started with the Plum Pudding model. So this was proposed by J.J. Thomson in around about 1904, and the reason for this model is that he wanted to incorporate two characteristics that were definitely known about the time of the atom, and that the first thing was there was no net charge for a neutral atom, in that they had the same amount of positive and negative charge. And also that there are negatively charged electrons in the atom. So that meant that the Plum Pudding model had this positive charge, which was described as being the pudding in this Plum Pudding model. And then it was known that the electrons were in the atom as well, and that there was the same amount of negative charge as positive charge, and that these were randomly distributed throughout the atom. And these were thought of the plum in the pudding. And don't forget that in a neutral atom, there is the same amount of positive and negative charge. So that was accepted from 1904 to 1909 when the alpha scattering experiment took place in Manchester. And this was undertaken by Ernest Rutherford, who directed Geiger and Marsden to do the following experiment. So they started with a radioactive source, and in particular it emitted a certain type of radiation called alpha radiation, which they knew were particles that were positively charged. They enclosed it in something called a lead collimator, just to ensure that all the radiation came out in a very known direction, a very particular direction, so all of the radiation was coming out horizontally. And those alpha particles, which were the projectiles, were directed towards a thin gold foil. And at the other end, there was some means of measuring the radiation, amounts of radiation. So at the time, it wouldn't have been a Geiger or Muller tube, but for the moment, if you were going to do this experiment in modern days, we would use a Geiger Muller tube. But it's just some way of detecting the radiation. And all of the experiments, all the equipment was enclosed in a vacuum. And the reason for that was two reasons, really. That means that the alpha particles are only going to interact with the gold foil. So that means anything that happens to the alpha particles is going to be due to an interaction with the gold foil. And also that alpha particles, because they're so highly ionizing, that they only travel around about 10 centimeters in air, and the vacuum then would allow those alpha particles to make it from the alpha emitter to the Geiger-Muller tube. So for those two reasons, all of that equipment was placed in a vacuum. So in 1909, what were Geiger and Marsden's observations doing this experiment? Well, given that at that time the accepted model of the atom was J.J. Thomson's Plum Pudding model, Geiger and Marsden should have observed the following. They should have observed the alpha particles passing straight through, undeflected. There wasn't really anything that they thought should have interacted with the alpha particles enough to deflect them in any way. And from that, they said that the positively charged alpha particles should pass straight through the thin gold foil. So that's what should have been observed. So why would they have done that? Well, it's thought that they would have done that because of the following reason. So here on the left-hand side, we've got the alpha particles, and we've got two gold atoms. And if we look at what should have happened, they should have passed through, straight through like that. And the reason for that was that in this model, there isn't a high enough concentration of charge available to deflect the alpha particles, which have got a positive charge of +2 because they're made up of 2 protons and 2 neutrons. And there wasn't anything really that interesting that should have happened if J.J. Thomson's Plum Pudding model was correct. Now we know that it wasn't, but why? So what did they actually observe? Well, they did observe that the alpha particles passed straight through, but it was a little bit more interesting than that. So firstly, most of the alpha particles pass straight through. So it's important that we say the vast majority of the alpha particles pass straight through undeflected. And what Geiger and Marsden then did, they started moving the radiation detector, or at the time it would have been a scintillator that they used. But if we move the Geiger-Muller tube around, what they also noticed was that alpha particles were deflected through an angle that was less than 90 degrees. And what I mean by that is those two angles there are less than 90 degrees. But more interestingly was that when they placed the detector somewhere around about here, they noticed that approximately 1 in 8,000 of the alpha particles were deflected through an angle greater than 90 degrees. And this was really strange for Geiger, Marsden and Rutherford. And at the time, they considered that to be so strange that they said it was almost like firing a cannonball at a sheet of tissue paper and the cannonball bouncing off the sheet of tissue paper. They just didn't expect the Plum Pudding model of the atom to be able to do that. So they had to rethink what the model of the atom was actually going to be. So why is it that the alpha particles did what they did? So here we've got our alpha particles on the left-hand side, and we've got our more accepted model of the atom on the right-hand side, with small gold nuclei. So if we now allow the alpha particles to go through, just like J.J. Thomson's model, get more to move, most of them do pass straight through undeflected, and that's what we would expect to observe in the J.J. Thomson's model, the Plum Pudding model. Some were deflected through an angle less than 90 degrees, like that, which meant that there was something very positively charged to be able to do that. A concentration of charge was required to deflect that alpha particle away. But more interestingly, 1 in 8,000 did something very strange, which was they were deflected through an angle that was greater than 90 degrees. And that meant that there must have been something bigger than the alpha particle with a concentration of positive charge. So these are the conclusions that Rutherford came up with based on those observations. So what were the conclusions based on those observations? Well, if we start with the first observation, that the vast majority of the alpha particles pass through undeflected, Rutherford concluded from that most of the atom must be made up of nothing. And that means that in terms of volume, so if we think about the atom as a sphere, the vast majority of the volume of that atomic sphere is mostly made up of nothing. The second observation that made was that some were deflected through an angle less than 90 degrees, and 1 in 8,000 deflected through an angle greater than 90 degrees. The observation from those can be grouped together, and that, well, the nucleus is tiny, so whatever was happening very, very rarely, and the interaction between the alpha particle and this nucleus was very, very rare, and therefore that was due to the nucleus being absolutely minute. Because they were deflected back, that there must be some sort of electrostatic repulsion, and therefore the nucleus must have the same charge as the alpha particles. Now, they knew that the alpha particles were positively charged, so Rutherford then had evidence to suggest that the nucleus was positively charged. And the final conclusion was that the nucleus must contain the majority of the mass of the atom. And he came to that conclusion because the alpha particle was deflected back. So it's a little bit like throwing a ball at a wall. The ball bounces back off the wall because the wall is more massive than the ball. So in this example, the alpha particle gets repelled back off this nucleus, and it's the alpha particle that gets reflected back. So whatever it interacts with must be more massive than it in terms of mass. So it's this nucleus is tiny, it's got a concentration of positive charge, but importantly, it contains the majority of the mass of the atom because it is able to deflect back an alpha particle. So this led to Rutherford's model of the atom based on these four conclusions: that most of the atom is made up of nothing, the nucleus is tiny, it's positively charged, and contains the majority of the mass of the atom. So we've got our atom and a tiny nucleus inside it, but these aren't drawn to scale. So to give you an idea of scale, which I'm guessing you've seen something like this before, you can imagine the atom to be a football stadium and the nucleus to be a pea in a pod. And if you placed that pea at the centre of the football stadium, the pea would represent the nucleus and the stadium would be the nucleus. And in between the pea and the rest of the stadium would be nothing. So in terms of size, the nuclear diameter is about a femtometer, or times 10 to the minus 15 of a metre, which is very, very, very small. And if we compare that to the size of an atom, that's approximately times 10 to the minus 10 of a metre. Now, atoms of different elements vary in size, but they're all of approximately this size, in the region of times 10 to the minus 15 of a metre for the nucleus, in the region of about times 10 to the minus 10 of a metre, with some variation depending on what elements is being discussed. But what that means is that the atom's diameter is about 10,000 times larger than the nucleus's diameter, which means that the atom's volume is 1,000,000,000 times larger than the nucleus's volume. And that's 1 with 12 zeros. So it's absolutely massive compared to the nucleus, or that in fact the nucleus is tiny compared to the volume of the atom. So Rutherford's model is very, very clear about what happens to the nucleus, and that it's absolutely tiny, it's full of positive charge, and it contains the vast majority of the mass of the atom. But from that, there's no real evidence concerning what the electrons are doing. So what Rutherford considered was that he treated them a little bit like planets orbiting the sun, and that they went around in little orbits like this. Purely because he didn't gather any evidence to say exactly what they were doing. And that was fine. People accepted that for a couple of years anyway, until in 1913 there was a new model of the atom, an improved model on Rutherford. And in fact, Rutherford was involved in this work as well with Bohr. But he was unhappy, or they were unhappy, with the arrangement and movement of the electrons in Rutherford's model. The nucleus was fine. It's the electrons that were the problem that was causing issues in the science community. And what they thought was the problem was down to the electrons. They predicted that the electrons, if they were in an orbit similar to planets, that they would lose energy, and as they lost energy, they would spiral inwards towards the nucleus, and they would last for around about a picosecond, if anything. And a picosecond is a very, very short period of time. Don't want to go into nanoseconds, but it's a thousandth of a nanosecond. And then the nucleus, or the atom in this form, would be very, very unstable. It would be stable for a thousandth of a nanosecond. And of course, atoms are stable. So this model of what the electrons were doing wasn't correct. And the reason why we know it's not correct is that as these electrons lost energy and they spiral inwards, the energy that they lost would be released in other forms. And it was thought that they would release that energy in the form of light. And what would happen was that as they spiraled inwards, they would emit a continuous spectrum of colours. And we would see red, orange, yellow, green, blue, indigo, and violet being emitted from these unstable atoms. And we just don't see that. So a more stable model was needed because they don't emit this type of continuous spectrum. Because instead, when we excite atoms, we observe not a continuous spectrum of colour, but discrete colours or discrete frequencies. And each of these emits a different pattern of lines, a little bit like its own fingerprint. And we see these lines when we look at stars, when we do experiments in the laboratory. We can use a spectrometer, and we can see these lines and these patterns, and we can see these discrete colours, these discrete frequencies, and they're not that continuous spectrum like it is on the top of this slide. So we knew that they couldn't spiral inwards because of the observations that we have of those particular lines and colours that we observe at the bottom of this slide. So a new model was needed, and that's what Bohr, with Rutherford, came up with. So they decided that electrons were responsible for these discrete individual colours that different elements produced. And they decided then that the electrons were going to move in fixed, stable, circular orbits, or if you prefer, energy levels. Orbits or energy levels are fine. And that these orbits were determined by quantum mechanics, which I'm not going to go into in this level at GCSE. Whereas planets orbit the sun due to Newtonian mechanics. So there's completely different rules to why these electrons are in these orbits. And so they're not like planets orbiting the sun. What was also allowed is that electrons can move up and down energy levels or orbits. But to do that, if they were going to move up to a higher energy level, they would need to absorb exactly the right amount of energy to move up to a higher orbit. But if they wanted to move down to a lower orbit or energy level, they would have to emit light or energy. So, for example, let's have this electron moving down through a large energy difference. So it's going from a high energy level to a low energy level. And when it did that, it would emit a large amount of energy. And that would, let's say, would be this blue line in this spectra. And then if we look at an electron that was only going to drop a small amount of energy, like this one here, a small amount of energy then is going to be emitted, and that could be responsible for this red light that's in this atomic spectra. And then we could have an electron in between being responsible for this green line. And I haven't done it, but there will be another one for that blue line. So different atoms have different energy levels, and electrons can drop down from all these different energy levels. But every time the electron drops down an energy level, light is emitted. And because all of the energy levels are different, you would get different patterns of lines on those spectra, and you have different elements have different atomic spectra. That's it for different models of the atom. Don't forget to subscribe to the channel, and I'll see you next time on Spiral Physics Education.